This is our week 2 tutorial session of this course Introduction to Stat Mechanics. Please join. Wait. Okay. So, as you know that in this tutorial session, mainly I'll tell you how to solve the weekly assignments. But before, I'll not like week 1 assignment. I'm not going to solve the entire assignment for you this time because there are similar questions in the assignments, and you can, if I just show you one example, I hope that you can get the others done by yourself only. So we'll get started with that week 2 assignment, but before that, as I was telling you that I'll be also adding some extra set of problems in as own assignments. It is like excluding that, except that assignment that is already given to you weekly. So there are some questions that I could not finish in the last class, so I aim to cover that first, and then we'll move on to the problems of this week's assignment. Okay, so basically if you have a problem at any moment with the solution or with the explanation I am giving, then just let me know and I'll try to clear that out. Okay, so we'll be now solving some. One second. Just let me go full screen first. So these are some extra problems that I'll now try to solve with you, and these are apart from the assignments that are given to you in the course. So the first problem is, so these are basically simple problems, mostly based on the week 1's content and content related to week 1 lectures, but later on this will be helpful for you because this gives you an idea of how to solve this kind of problems in general, so that later on when you have to appear for the exam or in general for the course knowledge itself, it will be useful. Okay, so let us start with a very easy problem that we have a perfect gas. So basically I'll write down the problem in a short form first, and then we'll solve its answer. Okay, so it is given in the problem that we have a perfect gas. The mass of the gas is 1 gram. So we have the system we are given is a perfect gas or an ideal gas, and the mass of the gas is 1 gram, and we are changing the state of the gas from one state to other state. So basically initially the gas is in the state A, let's say, where it has a particular pressure, volume and temperature. We know that these are the parameters, macroscopic parameters, that actually define the macroscopic state of the system that it is in. So basically when the gas is in state A, we say that its volume is VA, its pressure is PA, and temperature is T subscript A. Okay, and now it is said that the state is changed to a different state called state B. In that state B, the volume is the gas has changed to VB, pressure has changed to PB, and temperature has changed to TB. So basically these things are PV. By V we mean the standard volume, P we mean the standard pressure, and by T we mean the standard temperature. And all these three are the macroscopic parameters to identify a macrostate of the system. So you are given that the state or the macrostate of the gas has been changed from state A to state B. Then the question is that in that process how much is the change of entropy. So as you know that these kind of problems are already, not this one but similar problems, it's a change in entropy we solved in week 1 lecture contents. So the similar question I am giving to you now, that What will be the change in entropy? Delta S, we denote it by delta S. It is change in entropy in this process. What process? That is going from state A to state B. Okay. So if any one of you would like to contribute to how to solve it, then that is welcome. I'll wait for 2 minutes if anybody from the audience likes to answer the question. Otherwise, I'll go on solving it on my own without wasting much time. So, 1 second. Someone has joined the meeting, I think. Admit. Okay. This is recorded. Yeah. Yeah. So I was saying that whoever has joined now, I'll explain the problem once again, that we are basically right now solving some extra problems that are mainly based on week 1 lecture contents, and this will give us a general idea of how problems should be solved, and after we are done with that, we'll go on and have some idea on how to solve week 2's problems. But the question I have given in question 1 is that basically we have a perfect gas system, which mass of the gas is 1 gram, and the state of the gas is changing from state A to state B, where state A has a particular volume, pressure and temperature denoted by VA, PA and TA, and state B, the volume, pressure and temperature changes to VB, PB and TB. So in this process of changing from state A to state B, you are asked that what is the change in entropy of that process. Okay, so basically this is the question I have given to you. I was hoping that any one of you could try to answer or solve, at least tell me how to proceed with the solution. But if not, then I will just solve it for you on my own. Okay, so just let me change the. Okay. So basically first to answer these kind of questions, you have to know that what is the formula for the basic ground, not ground rule, but the basic formula for solving this question. So basically it is based on the first law of thermodynamics, right? So mostly the questions you will find uh, solving this kind of questions like entropy change. This first law of thermodynamics comes very handy because this is our main statement or main formula or main law that we have to follow. So it is that dq equal to du plus dw, right? So this is the first law of thermodynamics, where dw is the work done, du is the internal energy change, and dq is the heat that is being exchanged. Okay, and we know that dq can also be written as T times ds. So this is equal to temperature times the change in entropy. And dw, if the system is, let's say, a fluid system where the volume and pressure is involved and there is a change in the volume, then obviously the work done in changing the volume is denoted by pdv. So dw equal to pdv. So if you write it totally again, so it is tds equal to du plus pdv. Okay, and we also know how to calculate the change in internal energy du. We know that that there is specific heat Cp and Cv. Just someone has joined the meeting, I think. Okay, so we know that there are specific heat quantities Cp and Cv, where Cv we specify when there is a constant volume specific heat. So there is a subscript V in Cv, so it is just del U del T when V is constant. So this is U and this is at constant volume V. So by this we know that if we have to get du, it will be just basically Cv times dt and nothing else. So just substituting that in our main equation, we get TDS equal to CV is replaced by CV dt plus P dV. Okay, so this is the ground formula that we have to start with. And then because we have to ultimately get the change in entropy, so we will have to know ds, right? So ds equal to 1 by T CV dt plus P by T dV. Now look very carefully that in the first term you have the whole thing in terms of the differential of temperature, and in the second term you have the integrand in terms of the volume. So you have to work accordingly, that if you have to know the total change in entropy delta S in that process in going from state A to state B, then you have to take an integral of ds from A to B, right? So once you do that in the first term of the ds part, so you have temperature in the integrand. So that is easy. Basically we have to get CV out of the integral because it has no contribution in the temperature integral, and it is just dt by t. Now going from state A to state B, you know that the temperature has been changed from TA to TB. Okay. Now for the second term you get that there is dV, that is in terms of volume, but in the coefficient of that you have P by T. So basically you have to adjust a little, that you have to express it in terms of pressure and volume entirely, or in volume basically entirely, so that the parameters should match, so that you can do the integral. Just like in the first term you had dt by t, you have to express this term in terms of volume, so that you have a something to integrate with the integrand of dV. So how to do that? It is simple, that because we have an ideal or perfect gas given to us, we know the equation of state for a perfect gas. It is basically PV equal to RT, where R is the universal gas constant. So we just have P by T equal to R by V. So we have basically expressed P by T in terms of volume, and R is the universal gas constant. So we replace this thing over here in the second term, and thus we get R in outside of the integral because it is a constant, and then dV by V. Again going from A to B, you know that volume is being changed from VA to VB. Okay. So if that is the case, then you get total change in entropy delta S equal to, we have to do the integration. So the first term is basically ln T from TB to TA, and the second term is again ln V from VA to VB. So by simplifying this further, you get CV ln TB by TA, because ln A minus ln B will basically will become ln A by B. So that's what I have done here. And if this is the second term is the same, it is ln of VB by VA. So we have got our final answer, that our delta S in this process is equal to CV ln of TB by TA plus R ln of VB by VA. So you have got the general expression here. So this is the general expression that is calculated in terms of this problem, but sometimes questions are given like you have given the temperature that is being changed, that is you have given the value, you have been given the value of TA and TB or VA and VB, and then you have to answer the same question, that what is the value of the change in entropy. Then you have to just use this formula and just put the values of TB, TA and VB and VA in the form, and with the known values of the constant of R and CV, you will just get the exact value of the change in entropy for this kind of a problem. So this is a generalized case that will also help you if you are given particular numbers to the quantities. Okay, so this question is done, and then we will move on to our second question. Now this is also an easy question, but this is interesting. It is the question of how to rearrange the cells in different levels. So the problem is that, let's say you have been given a system that has 3 number of cells present, and in each cell there is some particular number of particles that are present, and it is also specified what is the energy of each cell. Okay, so let us write that down. So we have a system of 3 cells. Okay, so, and let's say it is then the number of particles in those cells have been given as N1, N2 and N3. N1 is the number of particles in cell 1, then same goes for N2 and N3. And energy of a single particle in each cell, energy of a single particle in each cell is given as E1, E2 and E3. Now you have been told that the values are known of N1 equal to 5, N2 equal to 3 and N3 equal to 2. So these are specified to you, that in the, if you draw the 3 cells, let's say in terms of the steps, so this is your cell number 1, this is your cell number 2, this is your cell number 3. Okay, and in the first cell you have 5 particles, 1, 2, 3, 4, 5. In the second cell you have 3, 1, 2, 3, and in the third cell you have 2 particles. And you have also been specified the energy of each cell for a single particle, that is E1 equal to 0, E2 equal to 2 and E4 equal to 4. This is, let's say, in joule units. It is per particle, remember. For a single particle that will be sitting in these cells, that will have energy given by this. So basically, if you note that this is the ground state which has E1 equal to 0. The next state has E2 equal to 2, and the third cell has E4 equal to 4. So in this kind of problems, always a rough sketch sort of an idea, sort of a thing to get the idea of how the distribution should be done is always, I think it always is advantageous compared to just manually solving it, because then you can just visualize the whole thing, that how they can be distributed as well. For many number of particles you cannot do that, but at least for when there is a finite number that can be counted like that, you can try and do that. Okay, so now the question is that there are some change in the particle number in each cell, which is given by delta n. So it is the change in particle number in each cell. Now this change is can be done or is allowed to be done with the condition that you have to make the total number of particles to be constant and the total energy of the system to be constant. Okay, so with the total number of particles and total energy remaining constant. Okay, so with that condition given, you have been told that delta n3 equal to -2. So what are the values of delta n1 and delta n2? So basically the thing is that you have been given a particular number of particles that are distributed in this manner, 5, 3 and 2 in that each of the 3 cells, and the energy for a single particle in each cell is given. Now you have been told that you have to maintain the total number of particles in the system and the total energy of the system to be constant, and yet you can flexibly change the number of particles in each cell. Like if you want to change the number of particles in cell 1, that means you have to make a change in N1. Then what is the amount of change that you have to do with that with these two conditions satisfied entirely. So that change is delta n1. Okay. Similarly, if you want to change the number of particles in level 2 or cell 2, then it is delta n2. That value you have to also get by maintaining these two conditions fixed. And for level 3, we have been given that the change you can make, or that is allowed for you to make, is already given delta n3 equal to minus 2. That means you can take out 2 particles from there, or that's why it is a minus 2. And so then, given you have been given the change you can make in level 3, so what will be the change in particles number you can make in level 1 and 2, delta n1 and delta n2. So this is the physical idea of the problem. If now you go on and mathematically solve it, then it is pretty simple, that just two conditions are there, right? So those two conditions will help us get it. So condition number 1 is that total number of particles in equal to constant, or n is equal to n1 plus n2 plus n3 equal to constant. And how much it is? It is 5 plus 3, I think, plus 2. Yeah, 5 plus 3 plus 2 equal to 10. That is constant. So if n equal to constant, then we know that delta n equal to 0. Derivative of n, it is just 0. And if delta n is 0, again we can express it in terms of delta n1 plus delta n2 plus delta n3 equal to 0. So we call it our equation number 1. Then there was a second condition. This is condition number 2. And what was that? It is that the total energy of the system equal to constant. That means if you have n1 number of particles in level or cell 1, then it is n1 times e1 for that level. Similarly, for second cell you have n2 times e2, and for third cell you have n3 times e3 equal to constant. Now, why I have multiplied n1 and n2 and n3 with e1, e2, e3 respectively? Because e1, e2, e3 are just the energy of that cell per particle. So you have to multiply it with the number of particles present in that cell. So by going with that idea, you can just again take delta E equal to constant, right? Now if that is the case, then you have just to take delta or derivative of this whole term. Okay. But here remember one thing, that E1, E2, E3, these are fixed. Like the energy of any level for per particle, these are fixed values. So these are not allowed to for you to change. That means you cannot change delta E1, that is 0. Sorry, that is 0. Delta E1 is 0. You cannot just change that. Or delta E2, that is also 0. Delta E3, that is also 0. That means you can just play around with the number of particles that are assigned to that cell, but you cannot anyhow change the energy for that cell per particle. So that's what you have to keep E1, E2 and E3 fixed. So if that is the case, then that will not be affected by the derivative or the delta term over here. So that this will remain as constant to the left, that is E1 and then times delta N1. Similarly for E2 times delta N2 plus E3 times delta N3. Sorry, this is not constant, this is delta equal to 0, because E equal to constant means the derivative will be 0. So this is equal to 0, and this will be our equation number 2. So now look carefully, that what you have got is basically you have been given the value of delta N3. So why not use equation number 1 to simplify it a bit, that you have delta N1 plus delta N2 plus delta N3 value was given as, I think, minus 2. So it is equal to 0. So we can express it like delta N1 equal to 2 minus delta N2. So let's say this is our equation number 3. Again, going to equation number 2 and replacing the value of delta N3 to be minus 2, you get E1 delta N1 plus E2 delta N2 minus E3 minus 2 E3, because you have substituted the value of delta N3 to be minus 2, so it is equal to 0. and I think you were given the value of E1, E2, E3, E1 0, E2 2, and E4, sorry, this is not 4, this is 3. E3 is 4, 0, 2 and 4. So simply E1 is 0, so this term comes to 0, goes to 0, and E2 is 2, so it is 2 times delta N2, minus E3 is 4, so it is 2 times 4 equal to 0. So what you got is delta N2 equal to 8. So 2 delta N2 equal to 8. So delta N2 equal to 4. Yeah, I think that is right. So this was simple, and if that is known already, then from equation 3 you know how to calculate delta N1. This is simply 2 minus 4, that is minus 2. That means again it is minus because you have to adjust the whole thing with the conditions that the total energy is constant and the total particle is constant. So you can just take out 2 particles from level 1 or cell 1. That is why delta N1 equal to minus 2. So if we just write it down, delta N1 minus 2, delta N2 equal to 4. This is plus 4, that means you can add 4 particles more to the cell number 2, and delta N3 equal to, it was already given, minus 2. So if that is the case, then what will be the new configuration? So initially you had 5 in cell 1, I think 3 in cell 2 and 2 in cell 3. So now in the new configuration you can take out 2 particles from cell 1. That means the new number of particles in cell 1 becomes 3 because you have taken out 2. This was before, this is after. Now again in cell 2, this is plus 4, that means you are allowed to add 4 more particles to cell 2. So there are already 3, so you can add 4 extra, that is total it is becoming 7. Sorry, what I am doing here. Before, after, 1, 3, 2 minus 1 second. Yeah. In level 3, you have taken out 2 particles, so then there are no particles left in level 3, so it is 0. So then you have got N1 prime, let's say I am denoting. I think someone has joined, let me just add that person. Okay. Yeah, so basically initially you had N1 5, N2 3 and N3 as 2, and now in the new case N1 prime becomes 3, N2 primes become 7, and N3 prime becomes 0. So again you see that previously there were 10 particles in total, and now also there are 10 particles in total. So you are not violating the condition that the total number of particles has to remain fixed. And also if you calculate their energy, total energy, you will see that that is also not violated. Let us just for fun check that. In this case you had known that the energy was, total energy equal to 5 times 0 because E1 is 0, then 3 times 2 because E2 was 2, and this 2 times 4 because E3 was 4. So this is 0 plus 6 plus 8, that is 14 joule in total. What is the energy total for the new configuration? It is then E1, because E1, E2, E3 should not change, so E1 times N1 prime plus E2 times N2 prime plus E3 times N3 prime. So this is E1 0, it becomes 0, plus E2 is 2 times N2 prime is 7, plus E3 is 4, but N3 prime is 0. So again you are getting 14. So that means our calculation is right. So E total is constant and N total is constant. Even after we have changed the we have rearranged the whole thing by shuffling some taking out some particles from one level and adding some particles to the other, but the total energy and total number of particles does not change. So this was this question that is solved now. So now this kind of problems, I think you get the hang of it, but let us try one more and then we'll solve a different kind. So this is not exactly similar, but follows in the calculation of microstates and these things, because these are very like permutation combinational sort of problems that you used to solve in your mathematics. That chapter was in class 12, I think. But this kind of idea actually comes handy when you have to calculate the number of microstates, and as from there you have to know that what is the most probable distribution or what is the entropy for that particular case, because there is a direct connection of entropy to the number of microstates. That entropy is equal to kb ln omega, that is the Boltzmann's version of entropy. In most of the cases, we'll just set kb to 1, so that Boltzmann constant we set it to 1 for our ease of calculation, nothing else. And then S just becomes ln omega. Okay, where omega is the number of microstates that we have to calculate from the permutation combination ideas. So similar problem I'd like to address here is that, let's say you have been given 6 different particles and they are distributed in 3 non-degenerate energy levels. So first let me write down the problem. There are 6 distinct particles that are distributed in 3 non-degenerate energy levels, and those energy levels are 0, E and 2E. Okay, so these are the 3 energy levels that the particles are distributed in. Then you are asked that what is the total energy for the maximum possible maximum probable distribution. So what's the total energy for the maximum probable distribution? This is the question. Okay, so now you have to ensure that you have read the question properly, because there are some hints given in the question. Often people confuse with not or overlooking those hints, and then the answer comes different. So basically you have to very carefully read the question, that you have given 6 distinct particles. I also pointed this out to you in our last class, that you have to first ensure that whether the particles are distinct or they are all similar. That means whether they are all identical particles, that means indistinguishable from each other, or they are normal particles which are distinguishable from each other. So that actually changes how you calculate the rearrangement. Okay, so here in this case you have been given 6 distinct particles. That means they are not identical to each other. You can distinguish them separately, and they are distributed in 3 non-degenerate levels. So non-degenerate means you have different levels of different energies. So you can see that none of these 3 levels have the same energy to other. So they are all different, 0, E and 2E. And you have to calculate what is the total energy for the maximum probable distribution. So you have to first understand that how to calculate the distribution that has the maximum probability to occur. And after you have known that, you can just get the calculation of the total energy by knowing that how much particle is in what level. That becomes easy then. But the main challenge is first how to know what is the maximum probable distribution. Again, this goes down to the boils down to the idea of how to calculate the number of possible microstates, and then out of that which one is the most probable microstate arrangement. Okay, so first of all, let us, for the pictorial purpose, let us draw our 3 levels. So this is our level of energy 0, this is our level of energy E, the third level is the level of energy 2E. Okay, and these are the 3 levels, and 6 particles are there. So total number of particles is 6. Now you do not know what is N1, N2 or N3. That means you do not know how many particles you should put in level 1, that is how what is the value of n1, how many particles should go in level 2 and in level 3. So these are unknown to you, but the total number of particles is given as 6. Now the thing you have to follow here is that what is the probability. So you know that the probability here for a particular distribution is the possible number of microstates or possible number of ways to arrange the system, ways to distribute the 6 particles in 3 levels multiplied by individual probability of each energy level per particle. Okay, so this is the number of microstate omega that you have to know, and the second part is already known because there are 3 levels, right? And so this particle thing will not be valid here, because you have to ultimately get for all the particles what is the probability for the energy levels. So let me remove that. So because there are 3 levels, so each level has equal probability to the other, so 1/3 is the probability for each level. And because there are 6 number of particles, so if you take probability of 1/3 for each particle, then multiplying it for all 6, you will get 1/3 into 1/3 into 1/3, and that's 6 times, so you will get 1/3 times to the power 6 because 6 is the number of particles you have, and 1/3 is the probability of each particle occupying each of the 3 levels. Okay, just okay, recording is going on. Yeah. All right. So I hope up to this was clear. So this is known to you, but what is not known to you is this omega, the number of microstates. This we have to calculate. Now again, this kind of problems has been solved, similar problems has been solved in earlier assignment. So it should not be difficult for you to get how I am rearranging the particles in this manner. So let us try that together. Okay, so again let me tell you that the omega will be just the total number of particles divided by n1 factorial, n2 factorial, n3 factorial. So it is n factorial divided by individual number of particles in each level factorial. Why this is so? Because this is again a typical standard problem on permutation and combination, because there are total n particles, so they can they can have a permutation in a n factorial possible number of ways into each other. But then there is a constant that in each level there is a particular number of particles that are n1, n2 and n3. So those particles can again rearrange themselves into each other by n1 factorial number of ways, n2 factorial number of ways, and n3 factorial number of ways. So to ensure that every possibility has been encountered or included, so then you have to take n factorial divided by these individual factorials. Okay, so now we have to know what is the maximum probability distribution. Now see that in the probability you have two parts. This one part is constant 1/3 to the power of 6, but what decides what value will be the maximum for the distribution is this omega. or the number of microstates. So the value of omega, that is maximum, will give you the maximum probability. That is clear to you, because omega is proportional to the probability for this case. And when the omega will be maximum, when this denominator term will be the minimum, because anyway the n is constant, capital N is constant to be 6, so we cannot change that anyway. So this is 6 factorial divided by n1 factorial, n2 factorial and n3 factorial. So the only way that omega can be a maximum is when this denominator of this factorial multiplication becomes a minimum. So when omega is maximum, then total probability is maximum for that distribution. That means that distribution has the highest possibility to occur, highest probability to occur. And when omega will be maximum, if denominator, that is n1 factorial times n2 factorials times n3 factorial, becomes a minimum. Okay, so this part is sorted. Then we just have to understand or see what are the different possible ways to distribute these particles. So this is one, that you have energy level of 0 energy, then E energy, and then 2E energy. These are the three levels. And let's say we make a fourth column to identify what is n1 factorial times n2 factorial times n3 factorial. So because there are 6 particles, right? So how can you distribute that? First of all, put all 6 in one level. So let's say 0, 6, then 0, 0. That means you put all 6 particles on the level 0, and then the other level remains empty. But then now this can have different possibilities, because even if you can place this all 6 particles in the level of energy E or the level of energy 2E. So like you can put it like that, 0, 6, 0 or even 0, 0, 6. All these 3 cases, you see that the product of these factorials remains the same. That means it is 2 of them are 0, so 0 factorial into 6 factorial. So 0 factorials are 1, so 6 factorial is 6 into 5 into 4, 6 into 5 into 5 into 4 into 3 into 2. So this is a value you can calculate for yourself, but this is 60. So this is 720. So this is the value of n factorial for this case. Then another arrangement way can be, keep one particle at one level, 5 particles at the different level, and leave the other level as 0. So this again can be done in several ways, like this. Then again you can change 5 here and all these things, all these combinations. But the moral of this all these ways of arrangement is that you still have 1 factorial into 0 factorial into 5 factorial. So you just have to understand what is the effective value of n1, n2 or n3 in these cases. After that, it does not matter that how many times they occur, because you cannot calculate all the times. This will be a huge number, so this becomes messy. But you can just have the idea of how the n1, n2 and n3 values can be distributed, keeping the total n to be 6. So this is again, in this case it will become 1 times 5 into 4 into 3 into 2. This is 120. Again, another possible way can be divided into 2 and 4. So it is 2 and 4 and 0. And then again multiple possible arrangements of that. But again this is 2 factorial into 4 factorial into 0 factorial. So this is 2 times 4, 3, 2 into 1. So this is, I think, 48. Some other combinations are also left to make it total 6. That is that you have to take 3 and 3 and 1 0. So again, further possible combinations of that, but this becomes 3 factorial into 3 factorial into 0 factorial. It is just 3 factorial is 6 into 6, it is 36. Now look for yourself, are there any possible combinations left for 6? 6 can be divided as, first of all, 0 plus 6, that we have covered just on the top. Then 1 plus 5, that we have also covered. Then we can do 2 plus 3, that thing, 2 plus 4, that we have covered also. And then lastly 3 plus 3. And also because there are 3 levels, right, so you can also do 2, 2 and 2. Yeah, so this is another possibility that we left earlier. So this is actually the answer to the question. So 2, 2, 2, if you rearrange it like that, so it gives you 2 factorial, 2 factorial into 2 factorial. This is 8. So if you now look at the values of the factorial multiplication, you will see that among all the products, only the value of this last combination is the minimum value of the denominator. So this is our minimum value. So if n1 factorial times n2 factorial times n3 factorial is minimum, then it makes omega to be maximum. That means the probability becomes maximum when the arrangement is like 2, 2 and 2 for the 3 levels. Now the question you are asked is that what is the total energy, I think, what is the total energy for the maximum probable distribution? But that is easy, because once you have known that what is the maximum probable distribution's possible arrangement, or how much particle are there in level 1, how many are there in level 2, and same in level 3, then it is not difficult to calculate the total energy. So the total energy for the maximum probable distribution Emax is just E1 times N1 plus E2 times N2 plus E3 times N3. So E1 was 0 and your N1 is 2. Then E2 was E, N2 is 2, and E3 was, I think, 2E, and N3 is again 2. So this is just 2E plus 4E equal to 6E. So this becomes our answer to what will be the maximum what is the total energy for the maximum probable distribution for this case of 6 particles and 3 energy levels. Okay, so this is a general trick that you have to use for this kind of problems. And since we have already covered this kind of problem, so I'll just do one last extra problem, and the remaining 1 hour of the classes time I'll devote to the new assignments. So this is our extra problem number 4. Now this will be a derivation sort of a problem. So this is not a sum type problem but derivation, but this sometimes this kind of derivation also comes in MCQ. Not derivation comes in MCQs, but the relation comes in MCQ options. But you have to know at least that how the relation occurs, because the problem I am going to give you is actually a very important thermodynamic equation in itself, just that we have to derive it starting from fundamental equations. So you all probably know, first of all, these two terms. One is this isothermal compressibility, K subscript T. So this is isothermal compressibility. And the expression of it, you should also know that this is known from thermodynamics itself, that it is equal to minus 1 by V del V by del P at T constant. This is the isothermal because the temperature here is constant, and because the term is compressibility, so it means that how much the volume is being changed with some particular amount of pressure change. So if for dP pressure change you have a volume change of dV, then you get the compressibility. Also you have to divide by the total volume, so it is just minus 1 by V del P, and because the temperature is constant in the whole process, so it is subscript T. Okay, and similarly you can also have another term, that is isentropic or adiabatic compressibility. This is isentropic, or sometimes also called adiabatic compressibility. Okay, because here the subscript is S. S is the entropy, that means S remains constant in this case, and the notation is same. This is just in minus 1 by V del V del P, and instead of T here the S is constant. And why this is also called adiabatic compressibility, for your knowledge, is basically because you know that from the first law of thermodynamics, dq was your heat exchange, that is equal to TdS, right? But if entropy is constant, that means ds is 0 and temperature has a finite value. So to make this valid, you have to take dq to be 0. That means if entropy is constant, you also guess that no heat is being exchanged from the system or within the system, from the system with the surroundings. So that means it is an adiabatic process. So that's why isentropic compressibility is also known as adiabatic compressibility as well. And the relations, thermodynamic relations you are going to prove is that prove these thermodynamic relations. Number 1 or number A is show TdS equals to CVdt plus alpha T by KT dV. So this is one relation. Then second question can be show TdS equals to CPdt minus alpha TV dP. Okay. And the third question is, that will be derived easily. Cp minus Cv equals to Tv alpha squared by Kt. So let me tell you, I had not given you the expression of alpha first. I messed it out. So alpha is nothing but the it is 1 by V del V del T at P constant. So it is the rate of change in volume with respect to temperature at a fixed pressure. So this is your volume expansion coefficient alpha. Volumes, not it is a volumes expansion coefficient at constant pressure. Now just get the idea that even if I am expressing the problem in terms of a hardcore derivation in this case, but actually you can also be asked questions like you can be given the value of any of these quantities, and then you can be asked to calculate the value of entropy change like ds. And let's say the values of all these quantities, the temperature change, or let's say alpha, kt, these values are already given to you and you are asked to calculate the value of ds. Then in this kind of case, when again in terms of problems where the change in entropy in a process is given to you to calculate, then depending on what type of problem it is and whether all the other informations required in the equation are given in the problem itself, that means the value of alpha or value of kt or value of cv, then you can just directly apply this formula and get the entropy change in that process. So basically it is a part of many different possible problems that can be given to you, but once you know the root formula of everything of those problems, so then it becomes simpler to actually address those problems. So that's why I chose to give you this problem in terms of a derivation instead of a regular problem. Okay. Similarly, you can also be asked what is the change in entropy in a process given all the other parameter values provided to you, like alpha, then Cp and these things, dp. So then you have to use this expressions in the solution. And then sometimes you are also asked to, this is very very famous, that the difference between the heat capacities at constant pressure and constant volume. So this is also can be given in terms of a standard parameters, sorry, it's not standard parameters all, but standard expressions. So basically consider this derivation as a part or as a root solution to all different kind of problems that are possible in terms of what is the change in entropy in a given process. If you are asked, then these will be useful for you to start with. Okay, so just let me see how much time is left. Okay, so we are almost reaching 1 hour. So this problem, after this problem, will be starting with the assignment 2. Okay, so let us focus on the derivation now. First of all, look at what is being asked to prove in question number A. It is TdS equal to Cv dt plus alpha T by Kt dV. So the trick is that you look at the integrands here, that is dt and dV. So by that idea, you have to understand that here the entropy can be taken as a function of T and V. Anyway, entropy is a function of the macro states of the system, right? So entropy can be expressed as a function of all the macroscopic properties or parameters of the system. Now macroscopic properties can be T, V or pressure, any of that, temperature, volume or pressure. These are the macroscopic properties. And the entropy can be a function of any of them. It can be function of all or can be taken as a function of any of the two also. So for this case, because in the problem, in the proof itself, there is given two, the integrands are given in terms of two properties. One is temperature and another is volume. So we do not need the pressure here. So we'll just take entropy as a function of T and V. So if that is the case, then you know that ds equal to, just you take the partial derivative, that del s del t at V constant T plus del s del V at T constant dV. Now just you multiply both sides by T, so it becomes T ds equal to T times del s del T at V constant dt plus T times del s del V at T constant dV. Okay, now you have to understand what is the first and the second part here. So this is the first term. So this is the term number 1 and this is our term number 2. So in the first term, it is very evident that this is the whole value of T times del T by del T at V constant will be Cv. Why Cv? Because you probably know that from the first law, dq equal to du plus dw. Now dq equal to tds equal to du plus pdv. But if volume equal to constant, then dv will be 0. So this second part becomes 0. And in that case, du is just Cv dt, because Cv is your specific heat or heat capacity at constant volume. So if your volume is being given constant in your problem, so dV becomes 0. So then the heat capacity at constant volume becomes just del U del T at V constant. So then obviously du becomes CVDT. So by that expression, because D equal to CVDT, you also get that CV equal to, yeah, so I was, where was I? Yeah, so here TDS, that was our DQ, equal to now only DU, which is our CVDT. So if that is the case, then compare these two parts. So you have CV equal to T del S del T. And in this whole process, your volume is constant, so you take a constant volume. Okay. So once you get that form, you just substitute here, that form here. So it is exactly the same form, right? T del S del T at V constant. So you just replace it by CV. So your total TDS equal to now CV dt plus there is a second term you have yet to simplify. This is T del S del V at T constant into dV. Now this part you have to um, make some changes to actually express in terms of alpha and kt, whatever there was given. And how to do that? You have to introduce the idea of, one second, you have to introduce the idea of another thermodynamic potential called the Helmholtz energy. So Helmholtz energy is generally a function of T and V. This is this is Helmholtz energy, not potential sometimes it's called, or Helmholtz free energy you can say. Helmholtz free energy. And it is a function of temperature and volume. So these are all thermodynamic knowledge. Thermodynamics, in thermodynamics you have basically learned about it. So if F is that, then you know that F is such that dF equal to just minus SDT minus PdV. Now I'm not going to explain or elaborate on how this is coming, because again this is a basic thermodynamics derivation. So just look it up if you have forgotten this part. So this is done, and here from you get that df, because f is a function of t and v, so df can be del f del t at v constant dt plus del f del v at t constant dv. Okay, and by law of partial derivatives, you get that if you take the derivative like this, first you take the derivative with respect to volume, and then within that you take the derivative with respect to temperature. Initially the volume is fixed, then on the second derivative the temperature is fixed. Then by the law of partial derivative, because f is a function of both t and v, you can just change the order of the derivative. That means you can now first choose to take the derivative with respect to t, and then you choose to take the derivative with respect to v at t constant, and again the whole thing at v constant. So it's basically you have interchanged the order of the partial derivative, but it is a rule that still the both the sides LHS and RHS will be remaining in the same value. Interchange the order of the independent variables in the partial derivatives. Once that is done, so then what is, from here you know that what is del f del t at v constant. So just compare. So if we compare dt coefficient of dt on these two terms of df, then you get that del f del t at v constant is nothing but minus s, negative of entropy. And if you again compare the values of coefficients of dv on both the equations, then you get that the value minus p is your value of del f del v at t constant. Okay, so with that knowledge you just replace it here, that this del f del t is replaced by del s del s now. So it is, so basically there are minus in both sides, so that will be eventually cancelling out with each other. So we will not put the value of minus in before s, so it is just del s del v at t constant. Again on the right hand side, you del f del v is minus p, minus is cancelling out with the left hand side's minus, so it is just del p del t at v constant. So here it becomes clear that you can also express del s del v at t constant as del p del t at v constant. Okay, so where we basically had this up to this. Here we replace it by cv dt and this part. So here you replace the first term by cv dt and the second term at del s del v at t constant, that you now replace by del p del t at v constant. So what is the total formula? Tds equal to cv dt plus t times, you replace this term del s del v over there, so t times del p del t at v times dv. Okay, now there is another thing that you, last thing that you have to use to get to the final expression, that is, someone has joined. Okay, so we are kind of in the middle of a calculation derivation over here, so just follow the steps I am doing very carefully because it is a large lengthy calculation. So this is our del p del t at v, which we have to transform into some other form so that we get to the final expression in terms of all these kt and alpha, these things. So you have to use the law of partial derivatives. That means if your you know that if x, y and z are three independent variables, such that there is a relation connecting all these three, that is f x y z, some function of x y z equal to 0. That means there is some equation that connects all the three independent variables. So in that case you can express any of those variables in terms of the other parameters, that is x can be expressed as a function of y and z. Similarly z can also be expressed as a function of x and y, and similarly y can be expressed as a function of x and z. So why I am doing this will be clear in a bit. So basically this idea will be useful in our transformation of the thing del p del t whatever we had over there. So if that is our case, then dx can be written as del x del y as z constant dy plus del x del z at y constant dz. And dz can be written as, from this z as a function of x and y, so it is del z del x at y constant dx plus del z del y at x constant dy. So basically just now replace the dz here so that you can get the total dx as, first term is unchanged, del x del y at z constant dy, plus the second term is del z, this was del x del z at y constant times the whole value of dz is del z del x at y constant dx plus sorry, del z del x at y constant dx plus del z del y at x constant dy. So basically you have, now take out the common terms. You have dy in both coefficient, two terms in dy, coefficient of dy. So it becomes del x del y at z constant plus this second term del x del z at y constant times del z del y at x constant. This whole thing is in common as a coefficient of dy, this term. Okay, so this and this term I have multiplied now, and the leftover term is this first term, that is multiply this by this, you get del x del z at y constant into del z del x. So del z del x at y constant dx. So this is the whole thing. So if this is the case, then dx in on the left hand side and dy and dx is on the right hand side. So to match left hand side with the right hand side, you clearly see there is no coefficient of dy on the LHS. So the coefficient of dy on the RHS should be set to 0. So this should be 0. And if that is true, then you get this thing equal to minus this thing, simplifying it out. So del x del y at constant z equal to minus del x del z at constant y and del z del y at constant x. And simplifying it further and taking all the three in one side, you get del x del y at z constant. Then because this comes to the left hand side, so you have to take an inversion of that to do so. So this is just del z del x at y constant into, this is again inverted, del y del z at x constant equal to minus 1. So this is your, from the knowledge of partial derivatives of such three independent variables x, y and z, which has some connection with each other as f x, y, z equal to 0, then you can write them in this form. Now why I was doing all these things? Because now I have to make a connection of that with our variables pressure, volume and temperature. So consider these three as three independent variables like x, y and z we did before. And these three also can be connected by a same equation of f, p, v and t equal to 0. And this equation has a special name, you know that. That is the equation of state in thermodynamics. This equation that connects all the three variables of temperature, volume and pressure, this is basically what is the equation of state, how that is expressed in thermodynamics problems. So basically they clearly also follow this relation as well. So then just by following the example of x, y and z, how they turned out, you can also write the derivatives of involving these three parameters in the same manner. That means you can write del p del v at t constant, del v del t at p constant, del t del p at v constant equal to minus 1, just like that. Okay, and if you have got that, then why we are doing these things? Because you have to transform this form of del p del t at v constant to some other form. So that's what we are doing. So basically we'll keep this part to the other side. That means it becomes inverted. It becomes del p del t at v constant, and the other part remains the same. So it is minus of del p del v at t constant into del v del t at p constant. So this was the thing we are looking for and doing all the whole calculations of x, y, z for. And once we have this knowledge, you can just put the value of TDS equal to what it was. It was CV dt. Just go back. It was CV dt plus T times del P del T at V constant times dV. So T times del P del T at V constant dV. So just replace the value of del P del T from the above box. It is just minus T times del P del V at T constant, del V del T at P constant dV. Now you just have to simplify to get it in terms of alpha and kt. Okay, so alpha, first of all, kt value, what was it? It was minus v del v del t at p constant. Can you see this here? There is this term already. Let me use another color. There is this term already common. Only there is a minus 1 by v that is missing. That can be compensated in denominator and numerator. And there is also expression of alpha in the RHS. So what was the value of alpha? Alpha was simply 1 by v, thermal expansion coefficient of volume. So del v del t at p constant, I think. So sorry, I have made a mistake here. That is, it is del v by del p, not del v by del t. So anyway, so basically that makes sense, because here you get the value del v del p is inverted in inverted form present in the first term, and this part is directly present here only. Okay, so you can just simplify this whole term to get in terms of alpha and kt. How? So just write this TdS equal to CV dt plus, first of all, let us take out the kt terms aside. So it is just take the minus alongside, because kt has a minus sign in it. So it is minus of 1 by v. We have to take not 1 by v, but because this is del p by del v is inverted, so you have to invert it again to get the original form, del v by del p t constant, and you add a 1 by v with it. And to compensate for that 1 by v, because there is no originally 1 by v present term in the equation, so you also multiply a 1 by v in the numerator. That is compensated then, and take this part outside in the bracket. And what is the remaining? There is also a t present, so keep that t, and the last part was this del v del t at p constant dv. Now rearrange again and take this 1 by v here with this and in a bracket. So again, this whole part is your 1 by kt, and this whole part is your alpha, and this t is left as it is. So simplifying it further, you get TdS equal to CV dt plus t times alpha by kt dv. This is our final form that we have. Sorry. Final form that we have obtained. So this is proved. So let us check that whether, because we have done a lengthy derivation already, let us check that whether this was the term we had been looking for in the question itself. Yeah, so you can see that exactly this thing is been derived now. So derivation is a bit lengthy, but the tricks, whatever is used, mainly is based on the derivatives and the laws of thermodynamics, so it is not very difficult. And by following the same pattern, we can also go on solving this equation number b, which is, I'll just, let me check how much time is there. Okay, so I'll not do the full calculation of the second equation, but I'll let you know the trick and you can check for yourself. So in the second equation, you had to prove TdS equal to, instead of CV, here it is Cp, constant pressure, then minus alpha times V times T times dP. So the trick is the same, that again you look at the integrand, it is dt and dP. So basically you know that you have to express your entropy in terms of T and P. Previously in the to prove equation problem number A, you had taken entropy as a function of T and V, but then also equivalent you can take entropy as a function of T and P, because that's what the integrants tell you in this case, in this proof. And once that is done, then the same thing can be followed, that that ds equal to all those things, that del s del t at p constant dt plus del s del p at t constant dp. Then just multiply t on both sides, so it becomes t ds t dt t constant dp. Okay, so again, by following this thing, because you have to get another thermodynamic potential here, a new thermodynamic potential, just like we had F in the last case. So we'll introduce a thermodynamic potential in terms of G. G is a function of T and P. It is called gives free energy. F was Helmholtz free energy, G is gives free energy, and G has a specific form, so that dg equal to minus sdt plus vdp. So we can know that if you take del G del T at a constant pressure, it is minus S from this previous term. You know that if you take the partial derivative now with respect to temperature, now with respect to pressure with at a constant temperature, it is V. Okay. So again you can follow the same form, that you first take the derivative with respect to pressure, then with respect to temperature, and then change the order of the derivatives, and it becomes same with the left hand side. So it is del G del P at T constant P. Then you just replace the values, that del P of minus S at constant T equal to del T of V. Just these values has been used, right, at constant P. That means what you get is del S del P at T constant equal to minus del V del T at P constant. So this part here, it can be replaced by this one. Okay, and for the first part, it is again Cp value. You have to know that what is the value of heat capacity at constant pressure. Cp is equal to del U del T at a constant pressure, and if dq equal to du plus dv, then in case of a constant pressure case, Cp dq is just Cp dt equal to du. So this whole thing is Cp equal to del U del T at P constant. So this is equal to TdS, right? So if that is the case, then your T del S del T at P constant is equal to Cp from these equation, from these two parts. This and this, equate these two, and you get this one. So just replace this directly on the first term over here. What was it? Yeah, this part. So this is just basically Cp, and this part you have to replace by the other and the derivative we have got over in the below equation. So you get TdS equal to Cp dt plus T times this thing you have to replace over here. So it is minus T times del V del T at P constant dP. Now here it becomes relatively simpler, because you don't have to do much further simplification. After this part, just directly use the value of alpha. You know the volume expansion coefficient, alpha is 1 by V del V del T at P constant. So clearly you see that term over here. So you just adjust all the terms so that you multiply by a V so that you get a V in the denominator. Then del V del T at P constant and dP. So this is equal to Cp dt minus V times T into alpha into dP equal to Tds. This is our theorem number or equation number 2 that is proved. Okay. This is again a very important thermodynamic relation. And now you also get the idea of the Helmholtz free energy and Gibbs free energy from these two cases. And for the last case you had been asked to get what is Cp minus Cv, the heat capacity difference. So you know that when pressure is fixed, so dP equal to 0. But the volume can change, right? Volume can change because pressure fixed, that cannot guarantee that volume will not change. So dV can be finite, not equal to 0. So in this case, if dP is 0, then we know that dQ can be simply written as only Cp dt. There will be no further term. Okay. But also dQ can be written as Cv dt plus P dV. This is just the first law, dQ equal to du plus dW. Because when pressure is fixed, then the entire dQ is Cp dt. But if pressure is fixed but volume is not changing, so dV part does not become 0. So you get the total two terms in Cv dt plus P dV as a entire expression of dQ. So by equating these two, you get Cp dt equal to Cv dt plus P dV. So simply Cp minus Cv equal to P dV by dt. Okay, and what is the known expression of dV by dt? You know that is in terms of alpha, that alpha equal to 1 by V dV dt, and here P is constant obviously. So here also P is constant because we already mentioned that the entire process is with P constant. Okay, so if that is the case, then just replace the value with alpha. So it is dV dt at P constant equal to P times alpha times if I am doing it right on Cp alpha T, just let me check. Sorry, there was a mistake that has been done. So basically not a mistake, but actually this is not the standard form that we were asked to get, because we had also Cp minus Cvs in terms of alpha and Kt both, right? So we also had to get Kt. For that we have to simplify further. You have to get alpha and Kt as so the right hand side is Tv alpha square by Kt. So we cannot use Pdv term. Instead we have to apply the expression we have got from the theorem number 1, theorem number A in this case. So that was your Tds equal to Cv dt plus alpha T by Kt dV, remember? So alpha T by Kt dV. So this is nothing but the expression A that we already proved. Okay, so this is proved already in part A. So once you use that, then just replace it over here, that Cp minus Cv is just plus alpha T by Kt dV plus it is just alpha T by Kt del V del T at P constant. So it is alpha T by Kt into alpha V, replace this here. So what is it? It is T alpha square V by Kt. So this is also derived that the difference in specific heat is just T alpha square V by Kt. So this is our equation number 3 that we have successfully proved. This I choose this I had chosen to derive because these are very important thermodynamic relations involving this all entropy and initial part that we had followed in earlier lectures. So basically here now we are done with what we had to solve for our earlier lessons. Now how much time we have left, because in the last lecture, last tutorial session, I had solved the total um, assignment for you, but actually you need to solve that assignment by yourself and submit that. So, and I think there is also some part of the grading that is dependent on the assignment that I did not check earlier. So from now on, what I will do is that I will not solve the entire assignment for you all in advance. Once the assignment deadline is over, like in our next tutorial, I'll be solving the entire assignment, whatever is left or whatever in which part you express your doubt. But in this tutorial, I'll just choose to show you the pattern, how the things are done, maybe a similar problem, and then based on that you can have the idea on how the other parts can be solved from the same assignment. Okay, so that the entire thing is not solved only by me, you can also contribute in the solutions. Okay, so that part we'll do here. And don't worry if you have some difficulties in solving the other questions, I'll anyway make the all the solutions in our upcoming tutorial. Okay, so that you can also, if you have done something by yourself, you can also review that and check and compare whether that is correctly done or whether what I am doing is different from that or same. So that parts those parts can be followed. So for now, let us focus on this first problem. So as I said, I will be solving one part maybe, and the rest of things will be done by you. So the part I choose to solve is the first part. So this is mainly basically the challenge. I think this part is a bit different in solving than the other two cases. The other two are pretty simple, so that you can all anyway do by yourself very easily. But for the first problem, I'll just show you how this is done. That this thing you have already known from the lecture of week 2, that if you have been given a function that is even function, that means fx equal to f of minus x, then this is the theorem that is provided to you already as a theorem. So this is true, this holds, you know that if you take limit lambda tends to 0 lambda and this whole summation part on the left hand side, it can be equated with the integral, continuous integral on the other side of the same function. So that means there is a connection that is being made with the discrete summation of the function and the continuous integral of the same function. And by using that theorem, you are asked to verify that if the function form is given differently, like in the first case you have been given the function is 1 by x squared plus a squared, and where a is greater than 0, then you have to prove that this equation actually holds, this theorem actually holds, that both LHS equal to RHS. And not only that, you have to also calculate the values of LHS and RHS, the value that we get from the equation, because in the options you can see that there is specifically the values are mentioned, okay, of LHS and RHS. So similarly, you have also been given two different functions here and in 2 and 3, and again in a similar form you have to calculate and make the theorem hold for those two functions as well, also calculating the values of LHS and RHS. So this is the statement of the problem. So let me now choose a page and show you how to solve. Okay, this will be a sample example. So this is our week 2. Assignment. Okay, so the first problem is that you have a function, even function, fx equal to f of minus x. So you can verify the function you have given in the first part is 1 by x square plus a square. How it is an even function? Because anyway if you put f of minus x, you see that it is still the same, because minus whole square is 1 again. Okay, so it is just f of x. That's why it is valid. Otherwise this theorem does not hold if your function is not an even function. Remember that. And the theorem was limit lambda tends to 0, lambda n equal to 1 to infinity f of lambda n equal to half of minus infinity to plus infinity dx f of x. This is our theorem that will be valid for this function, and we have to show that it is valid as well as get the values on both sides. Okay, so first let me start with the summation part, because that is a bit non-trivial compared to the second RHS part. That is a simple integration, you all can do that. But on the LHS part, if you start with, you get, let's see, you had f of x equal to 1 by x squared plus a squared, where a is greater than 0. Now in the LHS, you know that you have f of lambda times n, where n is the term on which the summation is done. M is the discrete integers 1 to infinity. So if f equal to lambda times n, and lambda is some other constant, where you have taken the limit of lambda tends to 0 on the extreme left. So you just replace x by lambda n in the form of the function. So it is lambda square n square plus a square, and this term you just choose to simplify this term somewhat, so that you can have a particular closed form to actually solve the left hand side summation, because you cannot go on summing all the terms up to infinity, n values from 1 to infinity, right? So you have to have a closed form of the function, so that you can apply some known formula function and get the value of the summation by using that. So that's what we'll be doing. We'll be dividing it into two parts. How to do that? So first of all, simplify this. So this will be a minus, sorry. Okay, let me go to the, yeah. So this is the minus. Why minus? Because we will take a square as I times a whole square. I is the imaginary complex quantity, where I square equal to minus 1, you know. So if there is a I square with a square, so to balance that minus 1 sign, you have to put a minus in between. So this is the same term that has been expressed by other means. Okay, why we have expressed like that? Because we want a expression of a square minus b square formula. So this is exactly in a square minus b square form. So you get that a square minus b square equal to a plus b into a minus b. So it is just lambda n plus ia into lambda n minus ia. Okay. So yeah, this is the case, and then you can also go on and express it like lambda n plus ia minus lambda n. So you take like that and just adjust the terms in certain way. So get on the numerator, if you put the terms outside the bracket, you see that this minus lambda n with the plus lambda n cancels out with each other, and you are only left with 2 times ia. Whereas in your numerator, originally there are no 2 times ia. So you just adjust that in the denominator by multiplying it by 1 by 2 ia. So simply the thing becomes 1 by 2 ia. And because we chose to do this kind of an discrete like arrangement, so we can just stick to that. That means lambda n plus ia divided by the whole term minus lambda n minus ia divided by the whole term. So what does it make out of, what do we make out of that? So this is lambda n minus ia minus 1 by lambda n plus I. This is not difficult. You know that the same term can be arranged in this fashion. Okay. So up to this we are done. And in the LHS we have basically limit lambda tends to 0, then lambda summation over n equal to 1 to infinity f of lambda n which now reduces because we have simplified it to some extent. So it is lambda. Now this 2ia, this is a constant term, so this comes outside the summation. Then summation over n equal to 1 to infinity to 1 by lambda n minus ia minus 1 by lambda n plus ia. Okay. So if that part is completed, so now we have to think of a way to actually, because we have now expressed this whole function in a closed form. So this is now in a closed form, right, after simplification. But we have to get it in a particular functional form so that we can directly get it value without much further difficulty. And there is a very well known standard function that has a value similar to that. And how can you know that this has a value similar to that is basically you have to just let me check what was the function value. Yeah, so the function we'll be using here is called a digamma function. So you know probably about gamma functions, right? So gamma function can be like gamma of, let's say, z, let's say, equal to, it has a particular standard form that it is 0 to infinity e to the power minus t, where t is a variable, then t to the power z minus 1 dt. So if z is an integer value or what, or some value, not integer explicitly, but then this kind of a integral value will give us gamma of z. And digamma function is nothing but, it is expressed as psi z. It is the first order derivative of the logarithm of gamma function. That's why it is called digamma, because you first take the logarithm of gamma, then you take the first order derivative out of it. So it is just giving you gamma prime z by gamma z. So in the numerator you have derivative of gamma function, and denominator you have just simply gamma function. So this makes our whole digamma function that is expressed by standard means as psi of z. So there are some known formalisms or formulas or expressions, whatever you say, of the digamma functions, which will be important for us to know here, because based on that we'll be getting our calculations forward. Okay, so the first thing that you need to know is that psi z can be expressed as minus gamma, this gamma is a constant value, minus 1 by z plus summation over n equal to 1 to infinity 1 by n minus 1 by n plus z. So this is an important expression involving the properties of the gamma function. Okay, so here the value of constant gamma is just, I think it was some 5 point, no, not 5 points, so 0.5772. It's a large number, it's a minus sign. So this is the constant value that you do not need to bother about, because this is anyway a constant value. But what you do need to observe is that you have exactly a term where there is a summation up to infinity on discrete numbers n, all integers from 1 to infinity, in a closed format, 1 by n minus 1 by n plus n, and that is exactly related to our digamma function's value. So this will be helpful for us to proceed, because in our case also you know that you have a closed functional forms almost similar to this, and a function and a summation of discrete integer numbers from 1 to infinity. So we have to use this digamma function to simplify that part. But first of all, how to reduce our expressional form in terms of this form, 1 by n minus 1 by n plus z. So let us play around this term a bit. This is 1 by lambda n minus ia minus 1 by lambda n plus ia. So lambda n minus ia minus 1 by lambda n plus ia. So how can you first of all play around with this form? So you can take out lambda as common probably, and then you are left with, first you have to get an n, right? So you have to take the lambda outside. So you have to take lambda as common, and then it is n minus ia by lambda minus n plus ia by lambda. So first part is done, that you have n only without any further coefficients multiplied, because I have taken lambda outside. Now this only is not sufficient, because in this case you have 1 by n and then n plus z. So these are all n plus z sort of terms, because you have plus ia by lambda and minus ia by lambda in both the terms. So what we can do is that we can adjust 1 by n in each, so that the first term is 1 by n minus, take this term 1 by n plus ia by lambda first of all, and then to adjust this first 1 by n, because this was not present, you take one other minus 1 by n, which goes inside the bracket, and that you take with the first term. So we have to take a minus to adjust the whole positive sign. Okay, so just check for yourself that this is exactly the function in the closed form that was in the last line. The only change we have made is that to keep it, to make it look like the digamma functional form, we have adjusted a plus 1 by n and minus 1 by n inside the brackets. Okay, otherwise the whole thing is the same function. So after doing that, we can now proceed with the total form, that it was lambda by 2ia into this thing, right? So let us write that LHS lambda tends to 0, lambda by 2ia into the whole form of the closed form function has been changed to now 1 by lambda. Then the summation starts in from 1 to infinity to 1 by n minus 1 by n plus ia by lambda minus 1 by n minus 1 by n minus ia by lambda. Okay, so this lambda and lambda cancels out. So you have been left with this term, that we have to know the value using the digamma function. Now let us go back to the digamma functional form. This was the form, right? So if you have to just take out this part, this blue line part underlined, then the whole thing comes to the left hand side. So it becomes psi z plus gamma plus 1 by z equal to the whole thing. So we can write psi z plus gamma plus 1 by z equal to its n equal to 1 to infinity 1 by n minus 1 by n plus z. Now here, to compare, if you look at here, so you will see the digamma function z here is nothing but plus ia by lambda in this term and minus ia by lambda in the second term. So you see that if you take plus z equal to plus ia by lambda, then you end up with n equal to 1 to infinity 1 by n minus 1 by n plus ia by lambda. This is equal to, what was that? Psi of z is now, z value is ia by lambda. So psi of ia by lambda plus gamma constant plus 1 by ia by lambda makes it lambda by ia inverse, right? This is one thing. And then for the second part here, you see there, this is n minus ia by lambda. That means here z equal to minus ia by lambda. So it makes it n equal to 1 to infinity. Then 1 by n minus, here the n plus z is basically n minus ia by lambda is equal to, from the digamma function's expression, now the z is psi of minus ia by lambda plus gamma plus 1 by z, but that z value is minus ia by lambda. So when you take an inverse of that, it becomes minus lambda by ia. Okay, so after having done that, we are almost reaching towards a final end of the calculation. So just bear with my steps that I have been doing, follow that. So it is lambda, limit lambda tends to 0, then 1 by 2 ia constant in front, so 1 by 2 ia And the whole term in the summation of n is now being replaced by the digamma function that we have calculated from here. So you replace it like the first term was this term, right? This part. So you replace it like psi of ia by lambda plus gamma plus lambda by ia, and the second part had a minus sign in front, so this part will come with a minus sign of minus psi ia by lambda minus gamma, and this minus minus plus lambda by ia. So here plus gamma and minus gamma constant terms cancel out, and you are left with by 2ia 2 lambda by ia plus psi of ia by lambda minus psi of minus ia by lambda. Now up to this part we have done properly. Now where we are stuck is basically, I think, yeah, we have to get the values of psi ia by lambda to actually proceed further. Just let me check if I have done properly up to this part. So 1 plus ia by lambda in, oh sorry, I had made a mistake in expressing that forms. Oh. Yeah, so basically we had to first start with another expression, that we had to use psi of z plus 1 equal to psi of z plus 1 by z. This is one part, and that is equal to our minus gamma plus sum over n equal to 1 to infinity 1 by n minus 1 by n plus z. So basically till this part I think we did fine, except that we had missed out this psi z plus 1 term directly, because anyway if you want to express this part only, so you can just take out this thing as summation over n equal to 1 to infinity 1 by n minus 1 by n plus z equal to psi z plus 1 plus gamma, right? Yeah, so until this part we had to do, and then so basically the thing we had done is basically we express this part. We do not need this part because ultimately the equation will become simpler if you use this form and replace this in terms of ia by lambda, the whole thing. So what it becomes is that limit of lambda tends to 0, then so you have to, where was, yeah, so this was 1 by lambda, then 1 by n minus this thing for plus ia by lambda, and then in the second case you had z equal to minus ia by lambda. So you had lambda by 2ia from the initial part, and then you had 1 by lambda and then replace the first term as psi of z plus 1 is plus ia by lambda plus 1 plus gamma, and then in the second term your z was minus ia by lambda, so it is minus ia by lambda plus 1 minus gamma. So this gamma and gamma cancels out and you have only terms left as this thing 1 by 2ia psi of, now look very carefully that you have already gotten rid of the summation of towards the n tends to infinity part. So that was a headache. So that part has already been replaced in the functional form of digamma. Now you have to use another important property of digamma functions, that is, so these properties you can directly get from internet or some PDF about, or some look up the properties of um, digamma functions. Otherwise you can also, from the basic formula that I had given you, can directly try and solve it by yourselves, that whether this property is actually being held or not. But anyway, for this case, let us take the property of digamma function, that um, psi of 1 minus z minus psi of z equal to pi of cot of pi z. This is another property. Property of digamma function psi z. So if that is true, then you know you can express the thing we had left. The last part is basically psi 1 plus ia by lambda and then minus ia by lambda, right? So you can simplify it further, as it is equal to lambda tends to 0, 1 by 2 ia, and then it is basically psi of 1 plus z. So what is psi 1 plus z? It is, let us look at that. Psi 1 plus z is equal to psi z plus 1 by z. So now it becomes useful that you express psi 1 plus ia by lambda as psi of ia by lambda plus 1 by z is lambda by ia, minus the second part remains as it is, because you have to have the term of 1 by z, psi of 1 by z. So just look at the terms now. So this is our psi z, sorry, this is our psi z, and this is our psi of 1 minus z, where our z is ia by lambda. Now we just have to use the second property we just got to know about digamma functions, that it is lambda by ia as it is, keep that. Then this is minus psi of 1 minus ia by lambda minus psi of ia by lambda in a bracket. So this is just your limit lambda tends to 0, 1 by 2 ia lambda by ia minus pi cot pi z is ia by lambda. So you have already almost reached the conclusive end. So it is lambda tends to 0 by 2 ia lambda by ia minus pi, this is cos ia pi by lambda, cot we express cot as cos by sine, ia pi by lambda. Now to simplify further, you know that because cos theta is equal to e to the power of I theta plus e to the power of minus I theta by 2, so if you replace theta by I theta, then it just becomes e to the power of, do it by yourselves, that if you just replace theta by I theta in the previous term, you get cos I theta equal to e to the power minus theta by e to the power theta by 2. And similarly, you know that sin theta equal to e to the power of I theta minus e to the power of minus I theta by 2i. Then again replace theta by I theta in the previous term, then you get e to the power of minus theta minus e to the power of plus theta by 2i for sin I theta. Okay, so just by using that information, those informations, you know that cot I theta, which is cos by sine, it is just e to the power of minus I theta plus e to the power of theta by e to the power of minus theta to the power of theta, and then here it was a 1 by 2i, so this is 1 by 2, this is 1 by 2i, so 2 and 2 cancels out, but the 1 by I here goes on the numerator, this is I, the rest is the same. So now just replace thetas by our IA by lambda, because eventually that were our argument in the sine and cos. So here this becomes limit lambda tends to 0, 1 by 2 IA lambda by IA minus pi, this cot thing that becomes I times e to the power of minus pi a by lambda plus e to the power of pi a by lambda divided by e to the power of minus pi a by lambda minus e to the power of plus pi a by lambda. Okay, so we are almost there. Now we just have to simplify it so that we can put the limit. So simplification can be done easily, that you get this lambda by IA same, just this part you simplify, you take out minus a pi by lambda common, so it is 1 plus e to the power of 2 pi a by lambda, again same on the denominator also, minus to the power of 2 pi a by lambda, so this thing cancels out, and then if you further simplify you get lambda by IA minus I pi. So this is basic calculation, you can probably also do that by yourself, but let me finish it if I have started already. So 2 pi a by lambda, so this adjust this minus 1 as plus 1 as minus 1 plus 2 divided by the power of 2 pi a by lambda minus 1. Here I have adjusted the minus sign below, so take this term, this minus can be taken as plus. So this is lambda by IA plus I pi. Now that separate it in two terms, it is 1 by, so this is this part cancels out in the first term, so this is just 1 on the first term, and the second term it is just 2 by the power of 2 pi a by lambda minus 1. Okay, if you take out all the terms in the bracket, then it is I pi plus 2 pi, there is a pi here, or yeah, I think there is a pi already, so there can be a mistake here and there because it is a derivation, because if I miss some parts in some step, just let me know if there is some part missing, but it is 2 pi I by to the power of 2 pi a by lambda minus 1. Up to this part we have done, and in the front of it we had 1 by 2 IA, right? So the whole thing becomes limit lambda tends to 0, 1 by 2 IA lambda by IA plus I pi plus I 2 pi by to the power of 2 pi a by lambda minus 1. Now because lambda tends to 0, so 1 by lambda tends to infinity. So here it is e to the power of some 1 by lambda, so it is e to the power of infinity, which goes to infinity, and 1 by e to the power of infinity, that becomes 0, right? So by that mean you get this whole term set to 0 by taking the limit, and in the first term, because lambda tends to 0, so this is anyway 0, so after all the limit has been put, so it is 1 by 2 IA into I pi, so I and I cancels out, so this is just pi by 2a. So this is our value of LHS that we have got by solving the discrete summation using digamma function. Now we have to also show that this is equal to RHS. What was our RHS? This is 1 by 2 of the theorem, that minus infinity to plus infinity fx dx. Now because it is already mentioned that fx is an even function, so for even function we know that the value from minus infinity to 0 is just exactly the same as the value of the integral from 0 to infinity, because they are the mirror images of each other, they are even function. So that's what we can do this thing as 2 times 0 to infinity. Just instead of minus 2 plus infinity, we get it as 2 times 0 to infinity, because fx is an even function. That's what this can hold, otherwise it cannot be true. So this thing can be done. So just do the integral then. This is a standard form of integral, 1 by x squared plus a squared dx. We know that it is directly the formula of 1 by a tan inverse of x by a. And then you put the value of 0 and infinity. So it becomes 1 by a tan inverse of infinity minus tan inverse of 0. So you know that tan inverse is infinity when the value of the argument is pi by 2, right? Because cos pi by 2 is 0 in the denominator, that makes the value infinity. And tan inverse is 0 when the argument value is 0, because cos 0 is 1 and sin 0 is 0. So it is again pi by 2a. So we have just derived that our LHS equal to RHS proved for the particular value of the function we have been given, 1 by x squared by plus a squared, and the value is also calculated as pi by 2a. Okay, so the first part has been done. Now I promised you that I'll do one part and the rest of the things are, so believe me, the rest all the remaining two functions are simpler than this calculation, so that will not be a problem for you to do. Just ensure that here also the functions are even, right? Because to the power of minus to the power of minus x mod x by a, that means it is an even function. And this thing where fx is 1 for minus a to plus a value and 0 otherwise, this is also an even function. So because these are all even functions, so definitely this theorem will hold. You just have to derive that and show that actually LHS equal to RHS. So do the same thing, that first solve the summation over n and try to simplify it to some known form, so that you can get the value of the summation, and then calculate the value of integral from the RHS, and then equate both the parts and see what is the answer that is coming. Okay, so how much time it is left? So we are already past the time of the tutorial for this lecture. Now because that I think the deadline of submission for this thing is, I think, 7th of February. So by our next week's tutorial will be solving the remaining of the problems that we could not solve in this week's tutorial time. Actually, I did not intend to solve it all by myself, because the other problems are already mentioned in the lecture resources, so you can just go through the lecture videos and try to solve it. There's no, and if you have some difficulties, then we can discuss and solve it elaborately in our next tutorial. Okay, so if you have some doubts from the problems that we have already solved in this lecture, you can just ask me in this tutorial, or else we'll just end the tutorial session here. Any doubts, anyone? Okay.
Actually, ma'am, I have one question to you. Oh, sorry. Actually, I understood what you have been telling all the way from last 2 hours. But actually, I was looking at second tutorial. You see the other question, like just after this question, there is a, like, when you have to calculate entropy and all that. That also has a huge expression. And
So the second problem you are saying.
no, even after that also, if you go a little further down.
So in this tutorial, the second problem that I solved.
No. Just question number 3 and 4, where you have written e to the power, like, s and function of
Acha,
u
acha,
comma
acha.
n, like that. No,
So
this is a
weekly
very,
assignment. Yeah.
yeah. So I mean, I just wanted to, if you could have, like, please at least one.
4, 5, and 4, 5,
Yeah,
and 6. This kind of problem is
yeah.
there.
So this kind of problem, actually, if at least one, I mean, at least part of the story, if you could have been told, then it'll be easy
Uh,
for us to solve.
I can show you how to do it in briefly, like not the
I,
full,
yeah. That will be helpful,
but I
ma'am.
can show you the way how to do these
Yes,
things.
yes,
So
yes,
basically, these are common in 5 and 6, I think.
yes.
So just let me see the expression. expression. So let's say we take question number 4, where this formula is actually entropy function that is given already in the lecture resources, and what is told here is that in the same just in this expression you have to set the values of epsilon j, that means the energy of each level as j, q equal to plus 1 because that is for fermions, and m equal to 4, that means you have four number of steps. So these things m, q, here also there is a q, and here there is a epsilon j that you have to replace by j, and write the same function again, and then you have to set the value of capital N equal to 2, that means you have been given two number of particles, then you have to get what is the value of s. Basically you have to get the integral done, and then by taking a log from this exponential you can get the value of s, right? This is the main problem that is given here. So let me go to a blank page first. Yeah, so how these kind of problems are done. So see, you have been basically given a integral, whatever the whole thing, even if I don't write explicitly, but let me write the first line. This is d theta by 2 pi in terms of one integral in terms of theta, the other is in terms of phi. Then you are given e to the power of I theta u plus phi n. This is capital U and capital N, total internal energy and particle number. Then j equal to from 1 to, now capital M has been set to 4 as per the problem. So I take 4, then 1 plus, so there is a q here which is 1, so it is e to the power of minus I theta, epsilon j is j, plus phi, and the whole thing to the power of 1 because q is again 1. This is our integral that we need to solve. Now first of all, the thing is very easy. You just have to start with, this part. You have to take out this part and actually get the what is the product that you get from here. You have to simplify this term, like disperse it out. How to do that is very simple. You just have to use the j values in each case. Like if you put j value is equal to 1, then it is just to the power of minus I theta plus phi. Then what is the next item in the product is 1 plus j value is 2, so it is minus I 2 theta plus phi, right? Similarly for 3 you will have 3 theta, and 4 up the last part you will be writing it as 4 theta. The phi part has no change. Okay, so without hesitating any further, you just have to like couple the whole multiplication out. So you can choose to do the multiplication by manually also, or you can use some soft Python or Mathematica. Mathematica can be easily doable to actually get the product, but the idea is that you have to explicitly get the whole product, so that now the entire expression you have to express in terms of some, because there will be a 1 also in the addition. So 1 plus, you will get some common of minus I theta times some part, then you will get u to the power of minus, or let's say even if you take in terms of phi also, you will get some coefficient multiplied by to the power of minus phi, then minus 2i phi with some coefficient, and these kind of things. So basically if you now choose to denote, for simplification, if you choose to denote e to the power of I theta minus I theta as a, and to the power of minus I phi as b, then in the whole multiplication, if you separate that out and elaborate the whole terms, then you will get, there will be terms coming as 1 plus some b times some function of a that are given, like say it can be a square plus a cube plus whatever comes as a coefficient of b. B means e to the power of minus I phi. Then you can have a coefficient of b squared multiplied by whole bunch of a values, where b square means e to the power of minus 2i phi coefficient you have to take out, and these things will make the whole expression. That means you have to express the whole thing as sum over some, let's say n m coefficient value denote it as a n comma m, then b to the power of n, a to the power of m. Why I am writing it? Because this is a general series expression for the thing you will be getting if you decouple the whole multiplication as a product. So this n and m are basically indices. Like say these n values can be 1, 2, 3 depending on what are the power of b. B can be b square, bq, etc. like I said here. And then a can also have all sort of powers like a square, a cube from the multiplication. So those values are m. So n and m values are both integer values, 1, 2, 3 whatever. M are these things, and a n m are the coefficients that are left with. This is a general expression. So after you express that, you just have to simplify it in the integral. You just have to use the standard form of delta function. So you know the delta function form. It is integral form is d theta by 2 pi 0 to 2 pi, then e to the power of, if let's say you have e to the power of I k theta, or in terms of, let's say, directly use the term that is given here. So if you have term like this, that u minus n theta, then this value will be delta of u comma n. So this is a canonical delta expression. If you have an integral expression like that, then directly you can equate it with delta u comma n, which value is 1 if u equal to n, and if u is not equal to n, then this delta function value gives you 0. So, and as you know this form of integral, then you can just substitute the product value that you have taken out as general sum over nm, anm, b to the power n, a to the power m, and just plug it in the main integral, wherever our main integral is here. So just plug it in here, and then you just separate out the integral in terms of theta and in terms of phi. So what we will get is that you will get a delta, canonical delta function in terms of theta, and a canonical delta function in terms of phi. Then again you have to simplify the canonical delta values, because in one term you will get a term like a canonical delta of u comma m, and there is a summation of m to the front, and then you have a capital M comma a m comma n. So these are basically indices that you have to adjust, and this summation can take you out the value of this I wrote a step wrong, so this is just let me correct it. So the idea is that you have to adjust, and the values of canonical delta will actually help you to adjust the thing. So let's say if you have a value of the indices, like you get a, finally you get a n comma m, delta n comma n. This is a canonical delta that you get from, let's say, one of the integral terms, let's say from phi integral. So there is a summation of m to the front, and then you have you will get a delta, canonical delta expression in terms of u comma m also. So what will you do is that, also there is a summation of n, I missed it. So that this part, if you take the summation of n, and common n is present in both the terms a and delta, so how to write that? You just write it like a of capital N comma m, right? Because this summation over n will be actually simplifying that further. That is how you express the canonical delta expressions. Like if you have some, let's say some other term x p comma q, and then delta p comma 2, and if you have a summation of p on the front, then you just express it like x 2 comma q. So this p value will be replaced by q by 2, and the summation will vanish. So this is the idea how canonical delta works. So the same thing will be happening here, and you will get the value of some value a n comma n, and the other part will also in terms of canonical delta. And because you know the value of n equal to 2, so you'll just plug in n equal to 2, or let's say directly 2 comma m, and delta u comma m. Again this is the same expression, so what it takes out is the value of 2 comma u, a of 2 comma u. And what was a? That you have to remember that the whole product we calculated, that e to the power of I something something here. This thing I told you that you have to disperse it out, that was generally expressed as a term of a n comma m, right, where b to the power n and a to the power m. So if a n m was b to the power of n and a to the power m, and we said that b is equal to simply to the power of minus I phi and a equal to the power of minus I theta. For simplification, I just wrote it in terms of b and a, otherwise it becomes a pretty huge term and messy to actually calculate. So it just becomes to the power of minus I n phi and to the power of minus I m theta. Okay, and from the product itself we will get to see that what is the if you have to choose what is, let's say, then in the question there is different values of u that you have been asked to calculate for. Let us go back to the question. Yeah, like say here the u value has been, first you have to check that what value is non-zero. Let's say you take each of the values of possible values of u. Let's say they have taken u equal to 4, so then u equal to 4 and n is kept at 2 fixed. So then if you have to check for u equal to 4, you just plug in the value of u equal to 4 in the expression of the coefficient. Like here you get, if you are asked u equal to 4 and n equal to 2 already given, then you just have the value of a, what was it, 2 comma u, right? So it just 2 comma 4. That means you have to take the coefficient with which you have e to the power of I 4 theta as a function, and e to the power minus I 4 theta, and e to the power of minus I 2 phi as another function. So in the whole, if you just decouple the total product, so then you will get to see that there are different terms in these multiplication forms, and the product that has a multiplicative multiplicative terms like this, then you can just take the coefficient to that, whatever the coefficient value is 1 or 2 or whatever, that part will give you the value of your coefficient a 2 comma 4, and that will be the answer to your integral. So if it is clear to you, or like it is a, you can only understand after you disperse out the whole product term, then just separate it out in terms of the Kronecker delta integral expressions, and then you will just get to know what is the final form.
Yeah, yes, ma'am. I think it's quite clear now.
It can be a bit like difficult to understand here, because here I am not solving the whole part, I'm just telling you how to solve it.
Yes,
But
yes.
once you decouple the whole terms, you will see term by term and match the coefficient, so there will be no problem. And by similar fashion you can do problem number 5 and 6. They are just same problems with different um, terms, I think. Otherwise the problem is same, and the rest of the two problems were are doable also, that is not difficult. So if you have problems there, you can just review and let us do that together in the next tutorial. Okay.
Okay, thank you, madam.
Okay. Okay, then let us end this session.